machine translation. In this lecture, because in last lecture I realized that I had cut away too many details, and then we have like 15 minutes free at the end of the 2 lectures. Then now I have tried to put a bit more of details, hoping that that's going to be useful. So let's see if I manage to give everything on time. But yeah. Okay, so trying to link what I am going to talk about now with the general theory or the general problem and technology of neural networks. So you realize that at the very first lecture we were talking about why neural networks, if they have been around since the 80s and earlier, why now they suddenly are the most useful or the most powerful algorithm in most applications. And the 3 main reasons that most people talk about, and there will be some people that don't agree with me or might add on or drop some other one, is that data, thanks to the internet mainly, is much richer now. The other one is that hardware, especially to the graphical processing units and to how much we like video games, hardware now is exceptionally good. It is a couple of orders of magnitude faster than CPUs. And then software. And software is the most interesting one, and the one where this course and similar courses focus on. And on the software side, the side or the part of the algorithmic technology that was most important to solve or that was most damaging the performance of traditional neural networks is the one that we are going to explain today, which is vanishing and exploding gradients. So some people, decades ago, realized that if you look at how the gradients backpropagate in typical neural networks, and this happens as well in modern neural networks, then the gradients tend to become lower and lower as you backpropagate them from layer to layer. So in the output layers, the gradients are big and they have sensible numbers, but as you go to layers closer to the input, the gradients start to become lower and lower. And as a result, layers near to the output, they learn very quickly and the others don't learn much. And what this will result on is that in traditional neural networks, the problem will get to the point that the first layer will learn nothing, and the top layers will simply learn to try to deal with the random linear, non-linear projections that the first layers do. It will try to deal with it to try to predict anything, even after you introduce all those layers of noise. So the first layers will simply introduce noise because they didn't learn, and that was the reason why more than a couple of layers didn't do anything extra in traditional neural networks. And now, since 2010s, or depending on who you ask, but in the last decade, they have been able to figure out a number of tricks to improve or ameliorate the problem of vanishing and exploding gradients, mainly vanishing gradients. But the ones, or the most important ones that really solve more centrally this problem, or more purely this problem, are gradient clipping to solve the problem of exploding gradients, and LSTMs and GRUs and other architectures, which are modifications of the recurrent neural network that create a memory test, what I call, because really that's what it is, a super hidden state in the recursive neural network. Okay, so let's examine why the problem of vanishing and exploding gradients happen. So the thing is that if you look at several steps of a recurrent neural network, this is a neural network, so in reality the neural network is only this, with this W feeding to itself, but we have unfolded it in time, as in 4 different time steps, which is what we always do in the backpropagation through time algorithm. And the thing is that if you start analyzing how much the loss of the final output depends on the hidden state from several steps ago, what you realize is that you calculate it, so that's how much the final gradient changes with respect to the hidden state of the first step. And if you apply backpropagation or the chain rule, you see that it unfolds into that. Then the second element, if you apply again chain rule there, it unfolds again into another one, and then unfolds into another one, up to when we arrive to the final state. So in the end, the gradient, or how much the loss depends or changes according to the first state, is actually a multiplication of many derivatives as there are steps in the computation, and at the end we have finally the derivative of the gradient of the loss with respect to the final state. And these multiplications, if you remember, these gradients are the ones that backpropagate in a neural network or backpropagate in the backpropagation through time. And if you generalize it, well, here it is what I just said. So the problem starts, before I go to general equation, so here the problem starts with the fact that these gradients tend to be quite small. They tend to be lower than 1. And or sometimes they are higher than 1, but the problem is that with multiplications, if you apply a multiplication over and over and over again to the same number, because all these gradients end up being the same, so all these gradients end up being W multiplied by the derivative of the transfer function, because the transformation that we apply in every step is exactly the same. So in the end, what we are doing is getting the same number and multiply it over and over again, multiplying it as many times as steps there are in the recurrent neural network. What happens with that recurrent multiplication is that if this derivative is slightly lower than 1, then it will quite quickly tend to 0. Because if you multiply 0.5 to 0.5, you have 0.25. If you multiply it by 0.5 again, it goes to 0.15 whatever, or 12 whatever. If you multiply it again, it goes to 0.06, and like that. So you see that it goes down very quickly. And if the number, the derivative, is slightly above 1, then it will start growing exponentially as well. 2 multiplied by 2, 4, then 8, then 16, then whatever, up to, in 10 steps, you have 1024. So you see very quickly what was the problem. And that doesn't only happen in the 4 steps example that we were talking about. If we generalize the equation, this one might be a bit the harder step to digest, but it is simply what we are doing here is the equation that we had before. We generalize it to, rather than having only 4 steps, we have n number of steps. The last step, we call it with I for indigo, and the older step where we are trying to calculate the derivative, we call it J for Yankee, for instance. And then what you get is that this derivative, the derivative of a hidden state with regards to the previous hidden state, for all the intermediate states between I for indigo and J for Yankee, get multiplied over and over again. If these derivatives were different and they were random numbers with mean equal to 1, it will be okay. But the problem is that because it is a recurrent neural network, the value of this derivative is, or it is not always the same, but it has a couple of elements that are always the same. So this is how the new hidden state depends on the previous one. If you apply the derivative here to calculate this element, you apply the chain rule inside, so you have the derivative of the sigmoidal or the derivative of whichever transfer function, but in all times it was always sigmoidal, multiplied by WH, because in the chain rule you get all this stuff outside, you derivate by this guy, and then everything disappears except for WH. Then, if you apply this equation to here, you plug it inside and, you don't even need to change variables. The variables already have the same, the T has already the same letter than there. You plug it here inside, and what you see very quickly is that in all the steps, this H WH is exactly the same because it is a recurrent neural network. It always applies the same multiplication. And this derivative, well, there is another funny thing with this, the derivative of the sigmoidal. But the most important one that is more difficult to get rid of is this W. Because this W, if there is a difference of 10 steps, then you apply 10 times. In an example of W equal to 2, you get 1024. In an example of W equal to 0.5, you get, the result is 0.000 whatever. And as with W. The other problem that we have in this equation is this derivative of the sigmoid. And the problem with the sigmoid is that its derivatives for all the domain of the sigmoid are always below that, much lower than 1. So if you plot the sigmoid, you have this stuff. So for all the area of the domain higher than 1 or whatever, this is the derivative is almost 0 because there is no slope. And the derivative for anything below -1 is always almost 0. And even if you go here to the center, here in the central point, let's draw this a little bit better. So when the domain is equal to 0, here the derivative is only 0.5, or was it 25? I think it is 0.5, but anyway, we can calculate it later. The important thing is that it is lower than 1. And this is only in the maximum point of the derivative of the domain. As soon as you go a little bit further from it, this starts being much lower than 1. So we have a double problem. We have that we multiply a number either smaller or larger than 1 many times as intermediate steps. And then we apply this other number, we multiply it over and over again. This number will change from step to step, but in all the steps it is going to be below 0.5. So we are fostering vanishing gradients very quickly and a bit of exploding gradients. And well, what I am saying here is the same. So when W is higher than 1, you get exploding gradients. When it is lower, you get vanishing gradients. And any questions so far? Because I realize one of the feedback I got is that I start rambling a lot and I don't ask anybody. So how is it going? Any question about yes? Yes, the sigmoid. Yes, so this diagonal, so your question is about the diagonal?
Yeah, like how the graph that you drew there, like, like what is representing?
Yes, so it is representing this sigmoid. So this little, I think this was delta or rho. Well, anyway, imagine that it is delta. That delta is the symbol for the transfer function. And traditionally, now there are other transfer functions, but traditionally, the transfer function was a sigmoid. And the thing is that in the sigmoid, so the domain goes from -infinity to +infinity, and the range, do we have some other, oh, we don't have more pens. Well, I will use this half-dying green one. In the range, it goes only from +1 to 0, but the derivative here, if you apply the derivative of the, you can also write it this way, the derivative of the sigmoid with respect to the input. So this will be the input to the sigmoid. The derivative looks something like this, okay? And this will be 0. So in the 0 point, you get to the maximum, which is, I think it was 0.5. And as soon as you go a little bit away from 0, it plummets to 0 in the range very quickly. So if you like equations, you will say that the limit of the derivative of the sigmoid with respect to x plus minus infinity, this grows to 0. And this happens very, very quickly. You don't need to go very far to the infinity very quickly. You get to the limit 0 very quickly. And the input of that sigmoid, it could be anywhere. So when you are learning, when the neural network is learning, the gradient, the backpropagated gradient will naturally push the activity of H of the hidden state away from the central point. So even if at the beginning, when you initialize the neural network, there isn't many of the hidden states, or there are many hidden states near to 0, they will tend to go away from 0 quite easily. Was that clearer? Good. Perfect. Yes? Which one? DI. This one? This is the diagonal. So that's because these W's, because we have written this with vector or matrix notation. I would like to have used my funny notation with the brackets to say the size of every vector and every matrix in the equation, but actually the size, this H is a vector with as many elements as neurons in the hidden state of the recurrent neural network. Yes? Oh, so this H, it is not only a single number. It is, imagine that you are using a recurrent neural network with 10 hidden units. So it has 10 neurons inside. Or let's do it with this example. In this example, we have 4 neurons in the hidden state. So in this example, this H will be a vector with 4 elements. And these W are all the weights that project those 4 neurons to the 4 neurons of the next step in the recurrent neural network. So that W, because H is connected everything to everything, it is a dense connection, this W is going to be a matrix with 4 columns and 4 rows. And then this H is a column matrix, but I usually ignore that in the. So they in this nomenclature they assume that the reader is going to magically know what are the dimensions. That's why I don't like too much this nomenclature. But what you do here is that you multiply a vector, a column vector by this matrix, and the result is what is going to be the addition, what is going to be the effect that the neuronal values or the neuronal activity of the previous step is going to have in the next step of the recurrent neural network. Yeah? And the same, so the result is going to be another column vector of also 4 elements. And here it is the same. Here imagine that the input is one of those embeddings that have 200 dimensions. So then this X is going to be a column vector of 200 elements. But then this matrix is going to have 200 columns and only 4 rows. And when you apply the matrix multiplication, what that means is that each one of these 200 inputs is affecting, by some weight inside this matrix, a little bit to each one of the 4 neurons of the recurrent neural network. And when you apply that matrix multiplication, W with 4 rows, 200 columns, X a column vector of 200 rows, then you end up having a very small vector of, again, a column vector of 4 elements. And this other guy, this one is a column vector of 4 elements. It is the bias. When you sum all of this up, you have a column vector of 4 elements. When you apply the derivative of the sigmoid, if you keep using the vector nomenclature or vector calculus, you again get a vector, a matrix. And then this diagonal will mean that you only want to get the diagonal elements of that matrix that you end up with.
Yeah, and the rest of the entries in the matrix is zero.
The what?
So is that just a diagonal matrix and the rest of the entries?
Yes. So, I didn't. So what the? Okay. Yeah, and then later you multiply by this other one, and you get the result. I think where you get the matrix. So maybe where you, what I didn't explain. So the input is a column vector, but when you apply the full derivative, the vectorial derivative of a vectorial function is actually a matrix. And that's true. That should be explained there. I should have realized that it is not that obvious. So if you have the derivative and also this function, it is a vectorial function. It goes from R4, because in the example we have 4 neurons, to R4. Because actually, this derivative of this function is equal to the derivative for the first hidden state, so hidden state 1 or neuron 1, the derivative of neuron 2, the derivative of neuron 3, and the derivative of neuron 4. Or if you want to be a bit more, you like writing, then this is going to be the derivative of the sigmoid divided by the derivative of H1 of the first neuron, and so on. But when you apply the derivative to a vectorial function like this one, you end up getting a matrix. Indeed, this will be, I am messing up a bit. Well, no, I'm not messing up. These are vectorials. But anyway, these derivatives, because this thing is a vector, are going to end up being equal to the derivative of the first element with respect to H1, the derivative of the second element of the sigmoid by H1, the derivative of the third element by H1 as well, by the first neuron. And here now we start again, but we change. We go with the first element of the sigmoid and derive by the second hidden state. Okay? So in every column we have the output, the domain, the range of the sigmoid, the first element, second element, third element, and in the rows we derive by the first input, the second input, the third input, and so on. So we end up like with a matrix. But then this function, this derivative, so the second output doesn't really depend on the first input. So in reality, all these end up going to 0, and you end up having only the diagonal. Yeah. So yeah, that's why they have the diagonal. Next year, I will put an extra explanation of why that diagonal is there. Any other question? Good. Okay, I have to speed up a little bit. And exploding gradients. So what's the problem? So we were talking that we have 2 versions of this problem. One of them is the vanishing gradient problem. The other one is the exploding one. So the problem when gradients become very high is that if you visualize gradient or backpropagation, or if you visualize what is the effect of the update function in the loss function, so here you will have one parameter, then another parameter. Also in reality this is going to be quite a multidimensional space. Then if you start applying one step after another, if suddenly there is a region of the domain of this loss function that has very high gradient, the update rule is going to send the next state of the parameters of the weight of the neural network very far away. And often, when you make such a big step, you end up in a region very far away from a sensible area of the parameter space. Talking a bit more theoretically, you end up outside the basing of attraction of this attractor, the attractor where there is the global minima. Or you might even end up, if this happens a couple of times, you end up with infinite values or not a number, or register overflow inside the hardware of the computer, so it totally messes up learning. That will be the problem with the exploding gradients. And what is the most common solution that people apply here? So it is very, very drastic, a bit brutal, but quite effective. The only thing that you do is that you keep monitoring whether your gradients are going very, very high, and you put some threshold that, as many other metaparameters of the neural network, you play with until it works well. And if the gradient or the norm of the gradient, because this is a vector again, if the norm of the gradient is going above a given threshold, then you simply clip the gradient. You clip it, so the vector of the gradient, you keep it in the same direction, but you reduce it until its norm is exactly equal to the threshold. So it is in a vector space point of view, you are simply shrinking the gradient vector until it has this length, a length equal to threshold. And all these other small mathematical machinery simply means that you want to keep the direction of the gradient vector pointing in the same direction. So if you divide a vector by its norm, you get a unit vector, a vector whose norm is 1, but that points in the same direction than the original vector. Any other question with this? Yeah?
How do you pick the threshold?
It is a metaparameter. You play with it until it works sensibly. And that it is frustrating, but that's the case with most metaparameters in neural networks.
Sorry.
Yes?
So can you explain again the line inside the if statement, like how they get cut? So like if they go too much out, if they go outside of the threshold, how do we normalize it back inside?
Yes. So the thing, if we draw it, let me see. I am going to check if we have a better marker. Give me a second. Oh yeah, we have quite a collection here. So if this is, much better. If this is the vector, the gradient vector, so this will be, or let's use it. What nomenclature? Okay, I am simply writing grad. So this is the gradient vector, and it is a vector itself, okay? There I am using pseudocode, and then sadly in pseudocode or in Python you cannot write mathematical symbols. You can in Julia, which is great, but not in Python. Well, anyway, that's a vector, and then this will be the 0 point or the 0 vector, so this is the original space. What you measure is actually the norm. So if we start using a bit of we mix pseudocode with mathematical nomenclature, this will be simply the norm, the how long the arrow is. And then you compare this against this threshold, th. So the threshold is a scalar. It belongs to R only. While this gradient, it belongs to R and as many dimensions as there are in the hidden state. Or, well, not in the hidden state, but rather in all the parameters of the neural network. If it is higher, then we cut it. Oh, what did I do with the cut? Anyway, we cut it until it has exactly a norm equally to the threshold. So you will end up having gradient is equal to the threshold itself. And a norm belongs to R, the threshold belongs to R. So this equation makes sense. Yeah?
Yeah.
Oh, welcome. Any other question, you can stop me in the middle and I will reply. If some of them, I don't know it from the top of my head, I can later consult Wikipedia and come back and look very smart by answering the question. Yes, so that's what we do. So if we don't clip gradients, we end up with this situation from time to time. If we clip them, we end up with this other result. Oh, I found it. So what will happen is that when you end up in a region with very, very high gradient, you keep advancing in the direction of maximum descent, but you don't make massively large steps. And that solves the problem quite effectively. And this one, I think, and now, okay, I have talked about the exploding gradient side. Now we are going to talk about the vanishing gradient side. So what is happening with the vanishing gradient? So, as I was saying before, if you keep multiplying, if to be able to get the derivative or the gradient, the derivative of the loss function with respect to the hidden state quite several steps ago, then you end up with many multiplications and they very easily go to 0. And you say, well, that might be okay. Simply you keep, so the top layers near to the output are going to learn very quickly, but once they have learned perfectly, you will think that the longer term relationships that are not captured when you learn only with the final layers of the final steps are going to start learning, because those other weights are going to be stop updating. But that doesn't happen, because what happens is that as this gradient starts becoming smaller and smaller, you will start having the gradient from steps that are closer to this other older step are going to really dominate the equation and are really going to, so this orange backpropagated gradient is going to be much larger than this other component of the gradient that you are getting from that step. And when you update this W, remember that you are not applying only the gradient of the last step. Usually you apply the gradient of all these different steps, or you advance one step at a time, and in every step you apply the gradient again. So what will happen is that when you update the weights of W such that the activity, the hidden states of several steps ago have an effect on the blue output, what will happen is that actually all the effect that you are able to modify or influence in H are going to end up having an impact in this other gradient, in the gradient of the step that is much closer to this one. So what is going to end up resulting is that no matter which hidden state you are updating or are influencing by updating W, that influence that you are introducing into H through the update rule is going to be simply the influence that maximizes or improves the best the loss only a couple of steps away or in the very same step. But that influence that you are putting into H is not going to reflect what is happening with the loss several steps later. Was that clear, or any question? Okay. And now we are going to see some examples of what happens. So this is a typical example. So you have when a person, or when I go to the shop, or when I am going to use the printer, I think it was, to print some tickets, there was no toner, then I went to the shop, and you can modify the example in many ways. I went to the shop, I found a friend and do whatever, blah, 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 then I arrived to the shop, they didn't have toner, I went to a second shop, got the toner, then I went back to my house, and finally I was able to print what? So a person will say, well, yeah, she was able to print the tickets, because that's what she was doing before. But the problem in a recurrent neural network is that tickets appears ages ago. And then the gradients, when you are backpropagating the gradients through so many steps, when the gradients arrive to tickets, they are almost 0. So they are not going, the W matrix is not going to be updated in such a way that tickets can have any influence here. And then the neural network is not going to be able to put tickets there. It is going to be, she was able to print her document, whatever is more sensible to put if you only read the last sentence. And this is other example, even in a smaller scale, which also happens, is that, and I think this was analyzed in one paper, then what they saw is that if you have very simple cases, like the food of the cats is whatever. So even in this case, so if you have a bit of a long memory, you will realize that the verb to be here should have should match with this singular, should be in singular case because the food is singular. But if you have very little memory and don't know what is going here, the only subject or the only complement of the name that you can think about is cats, and you will end up putting the form of the verb are there, the plural one. And linguists or the NLP people that want to be a bit more theoretical will name this as syntactic recency and sequential recency. Syntactic recency is to get the complement of the name that is closest but that it is syntactically sensible. And sequential recency is simply to get the complement of the name in this example that is closest, and that's it. Any other example about this? Any other question about these examples? Okay. And now explaining a bit more the intuition. Okay. So explaining a bit more the intuition. So there are two ways of understanding the vanishing and exploding gradients problem. One way is what I have been explaining so far, which is the backpropagation, the point of view of backpropagation. And the point of view of backpropagation is that when you apply the chain rule to the gradient of the loss with respect to a very old state, you get a couple of elements, W and the derivative of the sigmoid, that are, this one is lower than 1, but this one, as soon as W is higher or lower than 1, it is going to go either to infinity or to 0 very quickly. But you can also understand the problem, at least the vanishing gradient 1, which is the most common one, the one that emerges more easily, from the point of view of forwards propagation. So you will realize that in a recurrent neural network, this hidden state, which is what will allow us to know or to relate something from several steps ago to what happens now in this current state, this H keeps being modified over and over again. And to be able to keep something in H stable for many, many steps, you will need to put in this W, imagine that it is the second neuron. So in this W, the second row of the W will need to be almost everything 0, except perhaps you could put a non-zero value in the column corresponding to some neuron that has privileged access to that second neuron. And for the input, a bit the same. If you don't want the input to really have an effect in the second neuron, the second row of W will need to be totally 0, and the bias as well. And it is very difficult for a neural network to learn something so complex, to have the gradient in so many connections pointing to the correct direction. So how do we fix this problem? And I will need to speed up a bit. So how do we fix this problem? Well, the concepts, the idea with which we can solve it is by creating what is really like a super hidden state, so to speak. So it is a hidden state, which is called a memory cell, which is more difficult to write on. So the neural network will need to go through, by default, the neural network cannot write on it so easily. And the way you control that tightly access or writing rights to the memory cell is with several gates, a forget gate, an input gate, and an output gate. Well, actually, it is only the forget and the input gates, the ones that control writing. The output gate controls output, how the current value of the cell is going to affect the output of the recurrent neural network. And then when you put it into equations, the equations might look a bit confusing, but simply what you are doing is you get the previous state of the memory cell, you apply these gates, so these functions, transfer functions, are sigmoidal. Remember that activation and transfer functions, they are the same, different nomenclature. They go from 0 to 1. So when this input puts the output of the sigmoid close to 0, it means that we are forgetting the previous value on that neuron. So we are eliminating. So when we are putting the new value in cell memory at step C, we are not going to use much the previous the cell value at the previous time point. And then this input input gate, also from 0 to 1, what it controls is how a new, the result of a new mini neural network layer living inside the LSTM, how the result of that mini layer is going to be introduced into the new cell. So if this input is all equal to 0, then we are not going to put anything new into the memory cell. If for some neurons this input is close to 1, then whatever this new C is, whatever this internal layer is telling us, we are going to put it in that neuron. And then later, okay, so this was all the memory cell. Then later we also have a standard hidden state. The only thing that we do is to get the value of the memory cell. We apply another transformation, and we simply decide with this output that goes from 0 to 1 which of those values we are going to put in the hidden state, which is like a more output-like or accessible state. So if we now use diagrams to explain the same, so these are some diagrams, perhaps the most famous diagrams to explain complex recurrent neural networks from Colab website. I think it is that one over there. And this will be, using this type of diagram, this will be the traditional recurrent neural network. We simply get the hidden state from the previous step. We concatenate it with the input, also multiply by W and so on, apply a transfer function and send it to the next step as the new hidden state. So what we are doing now, using this diagram with LSTM, is doing a lot of wiring here. So we get the previous cell state gets certain transformation that are controlled by gates, and then later we put a new value in the hidden state according to the value of the cell, and those two things go to the next step. And now we go here a bit of explanation later as lecture notes for when you are studying after the lecture. And now let's analyze again using the diagram what I was talking about before a bit more quickly. So we have the memory cell, which is kind of a super hidden state. You realize that it goes straight through the LSTM, and then the only way to manipulate them is by putting ones into these sigmoidal elements. So for the neural network, it is not so super easy to write on it. The neural network can easily decide, I don't want to put any value here. Then the forget gate, the only thing that it does is that it concatenates the previous hidden state and the new input, makes some linear transformation with a weight matrix, puts it through a sigmoidal transfer function, and the result from 0 to 1 multiplies it with the cell. For the outputs that are near to 0, it erases the previous cell. Erases the previous memory cell. If it is close to 1, then it doesn't erase it. It allows the cell state to remain. Then the next input gate. So the input gate is like a double gate. It is later when we talk about attention, because this is a kind of really internal attention. So this is like another type of attention that I think they call it multiplicative or additive. I don't know. Next lecture we will see the nomenclature. So what you simply do is you have two different gates. In the sigmoidal gate, you do like in the for gate. So you decide when you are going to input stuff in the memory cell. And I mean when, because you only decide between 0 and 1. You cannot really widely modify the value. You can only decide whether you are going to put something in or not. then the tangent, the hyperbolic tangent, which goes from -1 to 1, is really the one that can introduce some information into the memory cell. And that's why conceptually, to distinguish between them, you can think of the sigmoid gate deciding when we are going to do something, to introduce something in the memory cell, and with the other tangential, which is like the sigmoid, but plus from -1 to +1, we decide what. The division is not that pure because both of them are doing a little bit of both, but if you want to simplify a bit to match the concept, then you can think of one decided when to write, the other what to write. Well, and this one I have been explaining it before. We modify forget and input according to those other gates. And then what do we do? So that was for the memory cell. What do we do for the hidden state? So for the hidden state, because we are not so worried about writing on it many times, then we simply apply, so we decide what part of the memory cell or what transformation of the memory cell we are going to put into the next hidden state. And with the previous hidden state concatenated by X, we decide when we are going, or for which units we are going to introduce new information, a new linear or non-linear transformation from the memory cell. Yeah, so any question about LSTM? Yeah, good? Okay. And then you will say, and why this very complicated method? Because it seems to be very irregular, the whole architecture. Why don't we make it more regular? Well, the case is that there are many different alternatives of how to control the access to the memory cell and exactly how to do it. And the other alternative to LSTM that is quite common is what they call the GRU. And the GRU is simply a small modification. So we simply replace, rather than using a memory cell and a hidden state, we use only a single hidden memory state. So we unify both states. And the other change is that we also unify some of the gates. So what we end up having is so you have again some wiring that looks again complicated, but in reality it is quite simpler, because rather than having a forget and input gate, you only have an update gate, which decides, because if you realize of the symmetries in the equation in the LSTM, then there will be many times the situation when you tell the neural network to forget a memory cell, a neuron in a memory cell, but then if the input, the input value of the input gate for that neuron is not 1, then you are not going to put anything new into the memory cell. So imagine for neuron 2, forget gate is equal to 1, so you are forgetting the memory cell, the neuron of memory cell, the neuron 2 of the memory cell, and imagine that the input gate is also equal to 0. Then you are not putting anything into neuron 2 of the memory cell, and that to some that might look like a waste of computational resources. To others it might look like useful, because in some occasions it might be useful to simply not have any information in certain cells, in certain neurons of the neural network. So what they did here was simply to unify them by forcing the forget gate to be equal to 1 minus the input gate, or the other way around, such that you do both things. Always that you forget a neuron, you introduce something new as well. And if you want to introduce something new in a neuron, you forcibly forget whatever there was before. And then there is the reset gate, that what it does is also to see if we add any extra information to the new hidden state or the new memory cell, and then you apply, and there are some other little transformations, like the main one that I am not mentioning, is that you don't have a separated hidden state and memory cell. You simply have a single internal representation. Yeah, okay. So, so this is what I was talking about before. So, for recurrent neural networks, it is more difficult to be able to preserve information from time step to time step. The LSTMs and the GRUs are able to solve most of the vanishing gradient and the exploding gradient problem, but they are not able to really solve all the problems that there are. So, and the rules or the home take message is that it is useful to start first with LSTM because it seems to be what tends to be a bit more robust. And if something, if you want to see if the GRU is going to be more efficient in your example, which not always is, but sometimes it is, you can give it a try. And it is a bit frustrating, but this is the case with most of neural networks because we don't have a strong theory of how they work and why they learn. And then we were talking a lot about the vanishing gradient problem, but does it happen in it is simply an NLP problem? Well, it is especially important in NLP because of the recurrent neural networks, but it happens everywhere, also outside NLP. Not so strong, but it also happens. So in feed-forward neural networks, like using vision and so on, we also have this problem. And they have some other tricks to use in feed-forward neural networks, which some of them conceptually, they are exactly the same as we are doing in the recurrent neural network. For instance, residual connections, a ResNet neural network, which if you use PyTorch or TensorFlow, you can download and use the predefined famous ones. What it does is, it does a little bit like the memory cell, but without any gate. What it does is to jump certain layers and, for instance, give to layer number 10 also the values that you have in layer number 7. And that way, the backpropagated gradients are able to skip some of the linear transformations that tend to produce vanishing gradients. And then batch normalization is another one. So batch normalization tends to work always very well. What it does is to foster, well, I don't have the sigmoidal drawn anymore, but what it does is to foster the inputs of the transfer functions to go towards the input equal to 0, because that's where you have the highest gradient. These are not the only solutions. These are not the only solutions. There are other ones. Another one that, with a very nice theoretical paper, they were able to show that it works well, is being very careful with the initialization. In traditional neural networks, they use it to initialize everything to 0 or to some happy function without much argument of why to do so. But then they realize some more theoretical, or people using more theoretical arguments, they realize that there are certain ways of introducing the initial values. You can do it with a normal distribution or a standard distribution, but if you set the standard deviation of those distributions, random distributions, equal to, I think it was 2 divided by fan in and fan out, which is the number of inputs and outputs, or equations of that type, then you are able to preserve much better the variance from one step from one layer to the next, and that seems to help a lot learning as well. Also, better activation functions. So before we were seeing that one of the problems that fosters vanishing gradients is the fact that the sigmoid function, which everybody loved in the 80s and 90s, has very low gradient, always lower than 1. So there are some very radical other different functions like the ReLU, which is totally 0 for domain smaller than 0, and after domain x equal to 0, it starts growing with gradient equal to 1, exactly 1. It is that simple. And it grows, it is quicker to compute, and it works, it tends to work, well, it works way better than the sigmoid. Other one is leaky ReLU. I have to change that, there is a mistake. There is leaky ReLU, which rather than 0, below 0, it has a little slope. ELU, which is a bit softer. Usually the rule of thumb here is that the worst transfer functions tend to be the sigmoids, except if what you want to do is a gate, like in the LSTM. The next worst is the tangential function, because at least you have negative values in the output. next one ReLU, and next one ELU. That tends to be the way in which people rate them. And then gradient clipping, they also use it in feed-forward neural networks. Then other ways in which they call these tricks is DenseNet. So DenseNet is a bit like a ResNet. What it does is every few layers you simply allow top layers to connect to the lower ones. And then the high-wide net, it is exactly or very, very much the same idea than the LSTM, but rather than doing it in different steps of the recurrence, you do it in different layers. So what you do is that you allow any layer of the neural network to have access to previous layers, but you control that access through a number of gates. So these different THC, they are gates like we had in LSTM. Okay, and then another trick, this one is quite simple. So we were talking, so all the examples that we have been giving here is a recurrent neural network that goes from left to right when they are reading text or when they are reading an audio signal or anything. But why? But in reality, the correlations, the information correlation between what we are writing now in these words and what happens outside that word, there are not only correlations with words that we wrote before, there are also correlations with words that we write later. So it is also very beneficial to put another layer kind of in parallel to the left to right reading layer that reads from right to left. And it does exactly the same computations, but in the other direction. It reads from back to front. And then the only thing you do to keep computing or conceptually is that you concatenate the results, and that's it. And people, so this is in equations, it is extremely easy. You have two recurrent neural networks, one of them reads from one direction, the other one reads from the other direction, but both of them end up having access to both of them, so to speak. So there is a lot of transfer of information between one and the other. Or, sorry, that architecture is not the standard one. In the standard, in every step within this layer, they don't access the other. But in the next layer of the neural network, in multi-layer recurrent neural networks, they can have access to each other. Okay, and you represent it like this. Of the modern language model architectures like BERT, they use this bidirectional approach because it almost always improves a bit performance. Yeah, and the next idea, okay, so that was, well, about the bidirectional recurrent neural network. Any question? Everybody happy? Good. Again, you can stop me if there is anything funny. Yeah, so the next step is, okay, so we have a neural network, a recurrent neural network with many steps in time, with many layers in time, but why don't we also add layers in the perpendicular direction, in the top direction, like we do in vision and in many other examples? And yeah, we can perfectly well do that. So what we can do, and you don't have any problem in the equations, it works perfectly well, is that besides the recurrence in the time dimension, we can really stack a second recurrent neural network on top of it, and then yet another on top of it, and as many as we want. And the gradients, when you want to calculate, for instance, the gradient of the loss with respect of this hidden state, with respect to this hidden state, you can very well backpropagate from here to here through all the different possible steps, and it is totally doable. Thanks to the backpropagation algorithm, because you temporarily store the gradients in each neuron, you don't really have a crazy overhead in computation. Yes, and something that shows that still vanishing and exploding gradients are still a bit of a problem in recurrent neural networks is that if you try to stack many on top of each other, you cannot go too high. So in vision, you can have like 50 layers or more. and it keeps working better and better, especially if you are Google and you have a lot of servers. But in simple multi-layer neural networks, you saturate the performance quite quickly with a few layers. There is the other architecture, which is the transformer recurrent neural network, BERT, which is the most famous of them, but there are also ULM, FIT, and some other traditional ones, GTP2, that are able to manage these problems and other problems that we still don't even know much better, such that they are able to work better with even more layers. And yeah, that's it. So the take-home message is that LSTM and GRUs are able to solve most of the problems that recurrent neural networks have. LSTMs seems to learn better, but GRUs are faster to compute and to learn. Then, to avoid exploding gradients, clip the gradients, and it tends to work quite well. Use bidirectional neural networks; they always work always better than the unidirectional. And then use also multi-layer neural networks if you have enough data. And that's it. You have some papers with some information of what we have been talking about, and that's everything for this first hour. So now we are going to make a little break, and then we will go to the next one. Any question anyway about the first one? Okay.